So we already checked out the linked list implementation of the queue. So let's take a look at what we'll have to do if we were actually implementing this with an array. Okay, so if we did that, then again, our front could be at the position 0 and so on, and we will be adding elements on the back. We will also be keeping a count. So if we enqueue element E, it will be right in here, right? And our count, as you can see, will increase. The issue now is that as long as we keep adding elements or enqueuing elements, they are going to come here, and that's really easy to do as long as we are within the boundaries of the array. And because remember, the array doesn't grow, right? But the problem is going to be to take nodes out of the front. We actually do have a couple of options. So if we were going to dequeue, we could just say, hey, I'm dequeuing, you get the element from here, you get it, don't, and then you somehow mark the areas of the array, the positions of the array that are no longer used because elements had been there and have already been removed. However, if we do this, that means that there will be less room in here to enqueue more elements into our queue, right? But this is actually an easier way when we don't have a lot of elements, or when our array is big enough, or if we know how many elements we are expecting. Okay, however, there is another way to do it, and that is a little bit more work, quite a bit of work actually. If we move the elements, if we switch them, each one of them, we move them to the previous position, right? As we take the first one, then we slide them, we just move them to the next position. So the problem in here is that if we have n elements, a lot of elements, let's say n, when n is really big, every time that we dequeue something is going to require a big O of n, of the number of elements just to remove one, right? Which is painful. Whereas it could be different if we actually do a linked list, or in here, it will require constant number of operations in order for you to dequeue something, right? But we have the disadvantage of the shrinking space to add more elements to the queue. Whereas in here, our space remains constant, but our big O to dequeue something is actually significant. So we have seen how to enqueue and dequeue, and if you have any questions, you know where to find me. But before we do this, I want you to take a minute to reflect on the following. What would be the big O of pushing and popping an element into a stack if we are using an array implementation of a stack? What's the big O of either or? Now, what would be the big O of the same, pushing or popping, but if we have the linked list implementation of the stack? Now, keep in mind they go in and out. Nodes are pushed and popped on the same end if we're using the stack. Now, think of the queue now and try to figure out what is the big O of enqueuing and dequeuing an element, both if you're using an array implementation of the queue or if you're using a linked list implementation of the queue. Keep in mind that being analytical and thinking about this is going to help you decide which ADT is best to use, if there is a known one that you could use, or it will help you create one that will actually be the best option for your customers now that you are becoming a software engineer.